This is the first video in chapter 13, and we're going to spend most of 13 talking about mirrors, but we're going to do a little bit of back to the future and just sort of, we got two look backwards here. We're going back to V equals lambda F, and we sort of did this one in chapter 12, but we're going to do it again. I want to know what is the wavelength of WEEI's radio wave. Well, WEEI transmits out of Boston at 850 AM. Well, what does AM mean? AM doesn't really have anything to do with anything. AM means amplitude modulation, and FM means frequency modulation, but they're irrelevant right now. What really matters is there's a hidden, they didn't show their units. They did not show their units. That F is going to be 850 kilohertz. 850 kilohertz. Okay, so we have our velocity. We want to find the wavelength, so we're going to say wavelength is equal to velocity divided by frequency. So our wavelength is going to be, what's the velocity of those radio waves going to be? Think about that for a second. Okay, velocity of those waves are going to be 3 times 10 to the 8th meters per second, which is the speed of light. And then we have our frequency is 8.50 times 10 to the 5th hertz. Think about how I got from there to there. It's very important that you understand for yourself how I got from that number to what I just wrote there. So my wavelength is going to be 3 times 10 to the 8th divided by 8.5 times 10 to the 5th is going to be 353 meters. Which is really, really long. That is that's you know, a little bit more. That's pushing 4 soccer fields. That's pushing 4 soccer fields. Okay, so we've done that before, and now another thing that I'm going to do in this introductory one, Back to the Future again, is we're going to go back to this equation, I equals P over 4 pi R squared, and we used that for sound, and we also said that it applied to light. And so I'm going to just go through a calculation really fast. Power output of sun is 3.846 times 10 to the 26 watts. The sun is putting out a lot of energy. And the Earth-Sun distance is 1.5 times 10 to the 11th meters. So the I, the intensity of sunlight hitting the Earth, is going to be 3.846 times 10 to the 26 watts divided by 4 pi 1.5 times 10 to the 11th meters squared. So the intensity of sunlight reaching the Earth, 3.846 to the 26 divided by 4 divided by pi divided by 1.5 to the 11th, 1.5 times 10 to the 11th squared is going to be 1,360 watts per meter squared. Okay, so now a lot of that is absorbed by the atmosphere. A lot of it is reflected back into space by clouds or polar ice caps which are going away. So not all of that is sort of available. So let's say, can we capture 5% of that? And that gets us to times 0.05, 68 watts per meter. Watts per meter squared. Okay. Now, current global energy consumption is, I found on the internet, they said about 1.5 times 10 to the 13th watts. So that means if I take those two and put them together, we need 1.5 times 10 to the 13th divided by my answer. We need 2.2 times 10 to the 11th meters squared of solar capture. However we're going to do that. Okay, so that sounds like a lot. Let's turn it into kilometers squared. Well, remember, there's like 1,000 meters in 1 kilometer, and then there's another, in this direction, there's 1,000 meters in 1 kilometer. And so there's actually 1 kilometer squared is equal to 10 to the 6 meters squared. So that means that this becomes 2.2 times 10 to the 11 minus 6 is going to be 5. And so then area of New Mexico is approximately 3 times 10 to the 5th kilometers squared. So if we wanted to capture sunlight and use that for our power source to meet all of our demands, we would need approximately an area the size of New Mexico, but we wouldn't need one area the size of New Mexico. We would spread it out over the entire globe. We could figure out a way to put it on the oceans or the deserts or all kinds of different things. And so we can do it. It's just a matter of political will to actually get around to doing it.